I'm sharing my slide for my presentation. Sorry. Today I will talk about the presentation on the practical sensitivity enhancement principle and the step impedance resonator based micro-biochip. Myself, Selim Reja, and my student ID is 2021160207, and I'm from Electronic Engineering Department. This research work basically miniature microwave resonator based ultra sensitivity mediator free biosensor for detecting the level of glucose in deionization glucose solution and human sera using IPD technology on gallium arsenide substrate. So in this technology, we used cross-couple step impedance resonator, and which strongly concentrate the electromagnetic energy by the coupling region at a certain central frequency, which is 6.35 gigahertz. And in this research, the changes in effective permittivity and permeability is shown, which is correlated with the variation of glucose concentration. If the glucose concentration is changed, the value of the effective permittivity and permittivity is also changed. And this effective changing equivalent to the conductance of the inductance and capacitance of the biosensor resonator. So with this parameter, we can saw the ultra sensitivity, which is 978.7 megahertz milliparameter load for the sera, and it also 4.918 faster and higher than the previous research work, which is explained. And in this research work, we also show the lower detection limit, which is almost 0.01982 micromole, which is so small, and the detected time is almost less than 5 seconds. And the previous research work, such as the Q factor based sensitivity, so there is a limitation, and this limitation also to be removed. And the limitation of the Q factor based sensitivity enhancement principle, I will explain. Q factor based sensitivity enhancement principle for microwave resonator based biosensor basically loaded the Q factor for the resonator, and it must be increased by the enhance the biosensor with this performance. And several studies we have to look at that the loaded Q factor with a planar microwave resonator, which is easier to design, fabricate, and suitable for biosensing experiment with the help of their structure, 3D structure, basically. And it also limited to the lower value with associated losses, such as the dielectric loss and the contact loss also. And these are the limitations of this the Q factor basis losses. So we should we try to be mitigation this problem. And the glucose biosensor using microresonator based loaded mediator line SIR. Basically, this microwave resonator biosensor application usable for detecting of the stress of the biomarker, human cell detection copy and biomolecular binding. And this application basically sensitivity inductive. For this application, the sensitivity is also changed with the indication of the shifting of the central frequency by the variation of the glucose concentration, and this is the most vital parameter we can see. And another factor, the low concentration level, which is avoid the interaction between among the glucose molecule, and it also important for the level free glucose detection. And the design, simulation, and fabrication of this biosensor resonator. Here you can see the cross-sectional, our proposed biosensor, glucose biosensor, which is fabricated on the substrate of gallium arsenide, which almost the 4000 micrometer gallium arsenide substrate. And these are the fabricated of this SIR or resonator circuit. And this first was the layout of the equivalent circuit, and here is the effective permeability and with the shunt capacitance. And there is also another factor for this of the horizontal direction in the effective permittivity with a inductance of series in the series connection. So there is a and the second picture is indicate the current density variation. Here you can see the color indications of this current density variation. And the C is also another image of this biosensor, which is the optical microscopic image. And this you can see, and from this we can see the cross-sectional view and SEM image of this resonator. And this is the cross-sectional view. This is the first layer, and the second layer AU or copper gold, the resonator cross-sectional view. And the image of another image of the additional and seed layer, which is also important for this making this biosensor. And this device geometry we have proposed it is basically consists of two cross-coupled dual section and symmetric SIR with the characteristics of impedance with the electrical length, with the impedance, characteristics impedance and electrical length. These are the Z1 and theta1 and Z2 and theta2. These are the input impedance with a variation of output and input impedance. And these are the ratio. And each of these SIR was minted with a widewise to increase the series inductance, and connected with a 15 ohm impedance for the matching of the transmission line. And this SIR internally loaded with the mediator line step to use the shunt and capacitance, and reduces in the signal losses for the transmission. And another issue for the dual section, and this symmetric SIR, this resonator condition indicated by the impedance, which is input impedance is almost zero. This can express in another issue. And the SIR optimize the parameter, almost the Z1 is 72.3 ohm, and the electrical length is 70.8 degree, and Z2 is the 70.5, 57.5 ohm, and and electrical length in the output section is 30.4, and Stop characteristics is 72.3 ohm, and the electrical length is 85 point, which is generated by the resonator with the central frequency, which is mentioned above, 6.53 gigahertz, and the loaded Q factor is 5.8. Basically, our proposed biosensor geometry allow the resonator to strongly concentrate the electromagnetic energy between the couple SIR, and which is simulated at the current density in the frequency 6.35 gigahertz. We have in this research the glucose sample preparation and S parameters measurement. And basically, this the glucose sample preparation two sections. One is the glucose stock solution, and another is the serum. This glucose stock solution are mixing with the deionized water with a D-glucose powder, and another sample is collected from the healthy human of subject, which is for measuring of S parameters. These glucose samples of different concentration with a 7.75 and 1, 2, and 3, and 4, and 5 milligram per mole, and the ranges of 75 to is suitable for the clinical test glucose selection. And the base level of this serum is obtained by the concentrating of centrifugal blood, or by the centrifuging of the blood at the 3000 rpm revolution per minute. The longer time for 12 minutes, and it was 1.48 milligram per mole. And to calculate the biosensor, this serum sample with the base glucose level 1.05 milligram per milliliter was supplemented with the solution of the D-glucose powder and with the deionized water to prepare this serum sample with the glucose concentration. And the concentration is variation is that there is a 1.05 and 1.25, 1.45, 1.65, and this are the all this concentration are in this measure. And to determine the analytical performance of this biosensor, the S parameters of this bare resonator was the first characterized by the over of a frequency range 0.1 to 10 gigahertz, and using the Alleganate 8501C, the vector network analyzer. And these are the basic. And another issue, the sensitivity enhancement principle. This in this sensor, when the RF electromagnetic or EM wave interact with the glucose samples, and this charge the samples moves and the dipoles also reoriented, and the electrical field is polarized with along the directions of the path of a biosensor, and as a result, this charge accumulates the opposite in the end of the biosensor. And this also the affected on the alternative the frequency of incident EMF wave, and so the new effective permittivity is introduced shown by the biosensor. And this also depend on the which amount or which concentration of glucose samples and frequency of EMF wave and geometrical structure we use for biosensor. And the effect of this capacitance and self-inductance lead the glucose level and which is changes the permeability, and the new effective the permeability is introduced, and it also depend on the glucose sample and as well as the frequency of EMF wave and the geometrical structure of the biosensor, and these are the uh, effective impedance and effective these are so the effective these are the effective permeativity and these are the permeability and this is the permittivity, and Z is the impedance and these are the impedance and the capacitance are in shown. And in this figure, the first is shows the symmetric proposed biosensor, which is shown the glucose detection and sensitivity enhancement principle and how it can going on. And then later on, we can see there is the VNA vector network analyzer. We can analyze by this micro dropper in the micro dropper level for the glucose sensor for the S parameter measurement. In this sensitivity enhancement principle, the combined variation of inductance and capacitance, and which is leads to the glucose level and it's also depend on the center frequency, which is denoted by the FC, and which is 1/2 pi f root over LC, and this is the inductance and this is the capacitance. We can see the before the lamp circuit. This glucose level is determined on the base of the amount of the shifting of central frequency of a biosensor bearing the glucose sample with the respective of a biosensor, and the sensitivity of the glucose detection can be increased by the enhance of the biosensor resonator with a net series inductance and the capacitance, and which is also the leads the enhancement into the sensitivity. So basically the sensitivity also changing with the changing of variation of the effective permeability and the effective permittivity. And the result and discussion, the detection of the deionized water and the glucose solution. Here we can see that there is the basic seven samples are almost shown with a different of glucose concentration, and there is a bare resonator and the measure of the S parameters and calibration of the curve are equivalent to the glucose solution 7.5 to 5 milligram per milliliter. And here is the one picture is shows as the central frequency changing, and the another is the linear regression with the central frequency and error bars. And then the resonator central frequency for different glucose level, and the mark here you can see a mark that its shifting point 3.1 gigahertz to its shifting point 3 hertz to from 1.5 gigahertz in the downing shift. This positive correlation between the downing shift of central frequency and the glucose concentration is causes by the interaction of the inductance, internal inductance, and the capacitance, and the based on complicated effect between the aqueous glucose and the sensor of this resonator. The glucose level depend and concentrate parameters. We study and analyzes of the nature of the shifting of the central frequency. And this is the effective permeability, and this is the effective permittivity. And the Z and N are the normalized impedance and the refractive index. And this is the refractive, this is the normalized impedance shown by this. And these are the S parameters using by the S parameters. And this is the refractive index by the using also S parameters. You can calculate this formula for these applications, and we study the shifting of the central frequency, and we also analyzes the effective permittivity and permeability. The glucose level depend inductance and capacitance are calculated from the measure of the propagation constant and the characteristics of the impedance. These are the L inductance and this capacitance, and this the propagation constant, and the this is the characteristic impedance. This the first graph shows as the glucose level depend effective medium parameters for biosensor resonator of glucose water glucose solution with the effective permeability, and this also shows as the B of the net inductance. And this is the net inductance, and this is the permeability, which is correlated. And these are the variations of different glucose and glucose shown in the level of different concentration. And these are the graph we can see. These are the almost one in this peak level, and this also we can see the increasing with this. This another we can see for the effective permittivity. These are the effective permittivity diagram or graph and result, and these are the shown for the net capacitance. These are the correlated we can see. And we also measure the S parameters and the calibration curve for the human's serum sample, and we can see the with the different glucose level the central frequency is shifting and different level. And also B is shows the glucose concentration and calibration curve obtaining by the linear regression of the central frequency and also the error bar. And the refractive index is almost 4, and the N is 4, minus N is 4. Basically, this biosensor resonator exhibit a and remarkable increase in the central shifting frequency. So the glucose concentration variation in the serum sample with the water glucose solution, and the shift of the central frequency is directly proportional to the change of glucose concentration via excellent coefficient and the linear regression equation. And we can see the measure of the samples, and we can found in hospital. We can collect it this for, and these are the RSD percentage, and the relative errors also shown and for the different level of sample. And this sample are measured for 4 times, and this is the central frequency equations we can for this. So these are the another issue. And the glucose level detection in the human serum, the depend constitution parameters of the biosensor. And this is the propagation graph is a Y, and this is the impedance of the graph. We can see it's almost the different variation and show the similar trend, increasing trend. And this is the peak level trend into this exception this. and the glucose detections by using the diaphragmometer. These are the net resistance for this biosensor with different six different concentration of the glucose, and we can compare this research work with the biosensor of the glucose biosensor by noticeable advantages of higher sensitivity, and is almost 4.98 times higher the previous work we have just discussed before with the microwave resonator based glucose biosensor. And we can see that is the comparison table. We can see this the microwave resonator base on the intertwined spiral inductor and interdigital capacitor. Our sensitivity is on 98 and LOD is 0.03, and the microwave resonator base with a rectangular mediator line resonator with a ER bridge. The ER bridge is 108, and the ER bridge enhance the capacitance base resonator is 61, and the nickel oxide to electro reduces graphene oxide base multi-wall carbon electrode 2082 is sensitivity, and this not found. So the lower number of metal layer, almost 2 metal layer, that reduces the device's fabrication complexity, and it also reduces the cost. And so the proposed biosensor almost proof that the rapid and simple and the robust. So the performance of this sensor is increased. So thank you from this all from my side. Thank you for watching my presentation. Thank you, Professor.